Okay, dear participants, welcome to this special session of the Third International Congress on Human-Computer Interaction, Optimization and Robotic Applications. Keynote speaker is Professor Ravi Agarwal from the Department of Mathematics of Texas A&M University in Kingsville. Firstly, I would like to introduce Professor Agarwal. He has been actively involved in research as well as pedagogical activities for the last 49 years. His major fields include numerical analysis, differential equations, difference equations, inequalities, and fixed point theorems. He has published 46 research monographs and more than 1,700 publications with almost 500 mathematicians all over the world in prestigious national and international mathematics journals. He has been ranked as a highly cited researcher for 14 consecutive years and has also been recognized as one of the world's most influential scientific minds in 2014 and 2015 by Thomson Reuters. In 2020, he has been listed among the world's top 2% scientists by Stanford University. According to the Google Scholar, Dr. Agarwal is cited more than 40,000 times, and on Math Science Net, his work is cited more than 16,000 times by 6,200 scientists. He has many notable honors and awards, including Doctoral Honors Causa by the University of Constanța in Romania, and Professor Honors Causa by University of Cluj, Honor Doctorates University of Nice in Serbia, Dr. Honors Causa by Plovdiv University in Bulgaria, Dr. Honors Causa University of Oradea in Romania, Dr. Honors Causa by University of Alba. He was also nominated as a possible candidate for a Banco Bilbao Vizcaya Argentaria Foundation Frontiers of Knowledge Awards, an international award scheme recognizing significant contributions in the areas of scientific research and cultural creation. Many Banco Bilbao Argentaria Awards winners are Nobel laureates, including Stephen Hawking, Florida Institute of Technology and King Abdulaziz University have recently offered him distinguished university professorship of mathematics. Professor Agarwal regularly disseminated his research at invited talks over 100 institutions all over the world. He has served over 40 international journals in capacity of an editor, honor editor, or associate editor. And it's also my honor to study together with Professor Agarwal in my postdoc study in the University Florida Institute of Technology. The title of his talk is Boundary Value Problems for Delay Differential Equations. And delay differential equations are used as a powerful tool for modeling, analyzing, solving, and discussing many different engineering problems. And you can start.
Thank you, Professor Mehmet Amir Koksal. My lecture is for 40 minutes or 1 hour?
45 minutes, and then questions, comments, and remarks.
Okay. So I will be talking on boundary value problems for delay differential equations. This is what is the abstract of my talk. We develop an upper and lower solution method for second order boundary value problems for nonlinear delay differential equations on an infinite interval. Sufficient conditions are imposed on the nonlinear term which guarantee the existence of a solution between a pair of lower and upper solutions and triple solutions between two pairs of upper and lower solutions. An extra feature of our existence theory is that the obtained solutions may be unbounded. Two examples which show how easily our existence theory can be applied in practice are also illustrated. Differential equations in which the derivatives of the unknown function at a certain time is given in terms of the values of the function at previous times are called delay differential equations. So this is a standard first order differential equation with delay where gt is less than or equal to t. That means the state of the particle is dependent not only on the present time, but on the past time also. Gt normally is t minus tau, where tau is a positive constant or it can be any complicated mathematical expression. The first paper I saw in this field was in Transactions of American Mathematical Society by Feit in 1921, Bornell in 1950, and then Driver, 1962, Driver again 63, and then Driver in 1963. These papers are considered the origin of delay differential equations. And I will say that for several years, these papers were considered as highly with respect. Then there was a book of Bellman and Kalava, Difference equations in 1963, S-Golds in 1966, Hino, Murakami, and Nato in 1991, and then Hale and Lunel in 1993. After this, I'll show you one or two more books. Delay differential equations occur in a variety of real-world applications, biological modeling, control of mechanical systems, economics, epidemiology, feedback problems, signal processing, neural networks, number theory, and psychology, and so on. There are several fields where these type of equations play important role. So as I mentioned, that from applications point of view, you can see Kwang book, Delay Differential Equations with Applications, and Hall Smith's book. Both of these books are quite interesting and quite popular. In last 50 years, qualitative properties such as asymptotic behavior, boundedness, oscillatory behavior, stability, etc. of solutions of delay differential equations have been studied extensively. Now, let me try to explain you with simple terms why qualitative property is interesting. Just consider a very simple differential equation, x double prime minus x is 0. It has no oscillatory solution. But if you change the x to xt minus tau, this equation has a x sine t solution. That means delay create oscillatory behavior, okay? And if you remove delay, then there is no oscillation. Thus, often the nature of solutions of delay differential equations is different from corresponding ordinary differential equations. This makes the study of delay differential equations different and more interesting. So you will find the books by Cushing, Ladde Lakshmikantam and Jang. This is the first book on oscillation theory. Giori and Ladas in 1991. This is the second book. And then Gopal Swami, he connected oscillation theory with the population dynamics. Irby, Kong, and Zhang, they published another book. And then we wrote a series of monographs on functional differential equations. The first one appeared in 2000, then 2002, then 2003, and then 2004. So we summarized in these 4 monographs whatever was known till then. In 12, we wrote a big monograph, myself, Brzezinski, and Brinkman and Dominsky. And we wrote a book which is quite popular. And another book which we have written is in 2014, Oscillation and Stability of Delay Models in Biology, that is in 2014. Now, when it comes to boundary value problems, the first paper which I have seen is in 1962 by Kaminsky. It is in Russian. And another paper in 1967, again by Kaminsky. And another paper by Aliyev, that is also in 1966. This is also in Russian. The first paper in English on boundary value problems for delay differential equations appeared in 1968 by Grimm and Smith. Another paper by Grimm and Smith in 1970. And this paper is the most popular paper in boundary value problems for delay differential equations. Then people started generalizing the results. For example, the paper by Spikas is in nonlinear analysis. Irvi and Kong is general computational and applied mathematics. Now let us see the problem when you try to compute the solution. Consider simple equation x double dash is equal to x t square. Suppose you take the grid points 0, 1 over 4, 2 over 4, 3 over 4, and 1. Okay. So second derivative we will describe, you will write down as standard, and then h square xti square. But you notice that t1 square and t2 square, what is t1 square is 1 over 16. But 1 over 16 is not your grid point. And if you choose t3, 9 over 16 is not your grid point. That means if you are following this scheme in order to compute the solution of this one, you have to compute the solution of those at those points also which are not in the grid point. Okay. So what happens that if this is not there, then in this case, you get a beautiful band structure, a tri-diagonal matrix. But because of this, you don't get the tri-diagonal matrix. So you get a arbitrary matrix. It depends how you will try to approximate these two values. So we started this study in 1973, and we wrote a paper, how to use finite difference method for second order functional differential equations. Then we extended this study in 1986, finite difference methods for boundary value problems of differential equations with deviating arguments in computers and mathematics with applications. Now, after second order, the problem was how to generalize the results. So first result which I took was in 1972, which was published in Journal of Mathematical and Physical Sciences, boundary value problems for differential equations with deviating arguments. So this is my first paper in 1972. And then there was a generalization of this paper in 1976. Tas Tasamatos, he published a paper on third order um, based on this work, and then we generalized further higher order boundary value problems for differential equations deviating arguments. Then there was another paper in 81, another paper in Rocky Mountain Journal in 82, and then there was a paper in 1995. Okay. Then there was another paper edited by, in a book edited by Johnny Henderson in 1995, and then by Paul Lillo Henderson, etc., in Pan American Mathematical Journal. So this became a multi-point problem instead of two-point problem, multi-point problem. So most of this work deal with boundary value problems over finite intervals, or for finite interval problems, there have been some existent results of bounded solutions. So what I'm trying to show you, till very recently, the study was only for either differential equations over a bounded interval or the solutions which were bounded solutions. Now, for ordinary differential equations, boundary value problems for second order differential equations on infinite intervals started by Wai and Zhang Fang, and then Floss and Tasmatos in RK mathematics. He studied existence of solutions of boundary value problems on half line to a second order nonlinear delay differential equation. Then Floss in Bulletin of London Mathematical Society, positive solutions of higher order nonlinear delay. So once again, bounded solutions were studied for higher order differential equations. While in recent years, the existence of unbounded solutions for boundary value problems over infinite intervals involving differential equations have been studied for several publications. For delay differential equations, not much is known. Existence and uniqueness of solutions second order delay differential equation on half line. This is in boundary value problems in 2008. Now, let us see what I plan to do in this lecture. I'm going to give you first for the second order differential equation minus u double prime t qt ft ut ut tau minus 1 ut tau minus 2 and u prime t. That means this differential equation with several delays. You notice that I have splitted this differential equation into two parts, in qt and then ft. My qt can be singular. You notice that it is defined over the interval 0 to infinity, but not at the point 0. So my q can be singular. Whereas my function f is a function which is a continuous function, okay? And tau, these are also continuous functions over 0 to infinity. So singularity is here, but singularity is not here. So this is the differential equation which I am going to consider. I'm going to assume limit t tends to infinity, t minus tau it is infinity, and I will assume that minus tau is minus minimum of t minus tau. So this is nothing but the minimum of all delays. That's what is the meaning of this one. We seek the solutions which satisfy the boundary conditions. This is the standard way of dealing with this type of problem. You find the integral representation of the boundary value problem. So I start with this differential equation, and I notice that here phi is a continuous function and a is a positive constant. It's any positive constant. And u dash infinity means limit t tends to infinity u prime t. Now for convenience, I'm going to write this in bracket, all this part. So this becomes, my differential equation becomes minus u double dash p t is same as qt ft ut u prime t. Now I define the lower solution and the upper solution. So this is the definition of lower solution. You notice that less than or equal to here, it is a strict inequality. I don't know how to change this strict inequality to equality till today. Okay. Similarly, we define the upper solution by reversing the inequality. And if you have inequality here and here, then it is called the strict lower and upper solutions. So this is the first problem which is not yet solved. Can I remove this A by 0? Can I remove this A by some constant? Can I remove this strict inequality? I do not know about these answers. Now I'm going to assume that my function, nonlinearity function, satisfies the Nagumo condition. So this is what is the Nagumo condition. It is nothing but a growth condition. So I assume that alpha beta be a lower and upper solution of the problem, satisfying alpha t less than or equal to beta t and minus tau to t infinity. We say F satisfies Nagumo condition with respect to alpha beta if there exist positive constants psi and h, such that f t u0 u1 un plus 1 less than psi t h modulus un plus 1. That means this is nothing but a growth condition, that the function is growing with the psi t and h. Okay. For all u0, 1 un plus 1, u0 is in this interval, u1 is in this, because this is what is assumed. So this is a sector. So all these ones are in the sector, but no restriction on un plus 1. This is in R. Now you remember my Q is in the differential equation and psi is in the Nagumo condition. I assume that the integral of Q of s, psi of s is less than finite, and I assume the integral of s over h ds is infinity. That means h of s has the power less than 1 asymptotically. So now we are prepared to write the solution of this differential equation. We have minus u double dash t z t ut minus a u prime t psi t phi t u prime infinity is c. This can be written in this form. The integral of this one can be written in this form, where g is the Green's function of this problem, which is very simple, a plus s and a plus t. S is less than t and t is less than s. So this becomes the Green's function, and the function is defined here. So this is between t, and t is between minus tau to 0, and this is when t is between 0 and infinity. So this is the way the solution of this one can be written. So here it is, g is the Green's function of this problem. Now we need a space. Let me go back to the differential equation. You notice that for this such a simple differential equation, if this part is 0, then ut behaves like a t. Okay, I'll repeat this one. If this part is 0, asymptotically ut goes to t. That means if this part you are adding as a nonlinear part or a linear part, you expect that when this part becomes 0, the solution should go to infinity. So what is required? A different space to deal with such a situation. So X is considered as a space of continuously differentiable functions from minus tau to infinity, and u prime t as t tends to infinity exists. So with the norm, this is nothing but the maximum norm over ut, and u1 is the supremum ut over 1 plus t, and this derivative is supremum of u prime t. You can check that this becomes a Van Arc space. So let the function Lt and g prime t be defined as follows. So this is my Lt, and this is my g head ts. Okay. What is important, that the boundary value problems can be written in the operator form. So for u belongs to x, we can define our operator in this form. So Lt is defined above, g prime is defined, g bar is defined above. So this is the representation of our differential equation in terms of an operator in the space capital X. Now, I'm not going to prove anything, just I will give you the hints. The mapping T defined in 9 has the following properties. If T belongs to minus tau to 0, then this part TUT minus A T U prime T is same as phi T. TUT is continuously differentiable on minus tau to infinity. The second derivative satisfies the differential equation not at the point 0, and fixed point of T are the solutions of 1 and 2. So this operator is equivalent to our differential equation satisfying the boundary conditions. So fixed points of this problem or this operator are nothing but the solutions of the boundary value problem. Now we want to apply some fixed point theorem, but in order to apply fixed point theorem, we have to be a little bit careful because it is an infinite interval problem and we don't have any control over the delays. So we have to be a little bit careful. So in order to use order fixed point theorem, we need what is known as generalized Argela-Esculi theorem. This you can find in our book written in 2001. So see the statement of this book. The statement is M is a subset of X. Let us assume M is a subset of X, is relatively compact if the following conditions hold. Number one, all functions from M are uniformly bounded. Number two, all functions from M are equicontinuous on any compact interval of minus tau to tau infinity. All functions from M are equiconvergent at infinity. That is, for any given epsilon greater than 0, there exists a T which depends on epsilon such that for any U, the following holds. So what we need is a subset of X which is relatively compact. For this, you need to satisfy all these conditions. Now, suppose the following conditions hold. Boundary value problem 1, 2 has a pair of upper and lower solutions. Alpha t is less than beta t on minus tau to infinity, and F satisfies Nagumo condition with respect to alpha and beta. Okay. Nagumo condition I have already introduced. Upper solution, lower solution I have already introduced. Here I am assuming alpha t is less than or equal to beta t over minus tau to infinity. Then the second condition is there exists a constant gamma greater than 1 such that this condition is satisfied. Qt is in the differential equation, psi t is in the Nagumo condition. So this condition must be satisfied. Okay. Then there exists a constant R such that every solution of 1 and 2 with U between alpha t and beta t satisfies U prime is less than R. Okay. What it says, what this lemma says, that if you have a solution of a differential equation which is between alpha t and beta t, then the derivative of this one is bounded with R. Okay. Under these hypotheses, if you have a solution which is bounded between alpha t and beta t, then the first derivative is bounded by R. The proof of this one is in 2 pages. And as I said, that I'm not going to show you the proofs. It requires the lemma I have stated here. So you need to satisfy the requirements of the lemma. A similar proof as of lemma 4 shows that the upper solution modulus is less than R, lower solution modulus is less than R. So lower solution is bounded, upper solution is bounded by R. Similarly, the derivative of the solution is bounded by R. Okay, this is the main theorem. Let us see the hypothesis. Suppose conditions H1 and H2 are hold. Further suppose that for any fixed t and u0 un plus 1 in R, when alpha t tau I t less than ui less than beta t minus tau it from I is 1 to n, this condition is satisfied. That means the function is your ut and alpha t are such, when this condition holds, then the function is satisfying this condition. It is a sort of monotonicity condition, but you notice that un and un plus 1, there is no restriction. Okay. Then the problem 1, 2 has at least one solution, which is continuously differentiable from minus tau to infinity, twice differentiable over 0 to infinity. 0 is not included because our differential equation is singular at the point 0. And it satisfies ut is between alpha t and beta t, and u prime t is less than or equal to r. Now let us see a little bit about its proof. What I do, I define a modified function, or rather I truncate the function. How I truncate? I define f0 in this way. You notice that you have here u1 tilde, un tilde, here you have beta, you have un plus 1. So I'm subtracting something when u0 is greater than beta t. Okay. I'm not touching u0 if u0 is between alpha t and beta t. Okay. I'm replacing u0 by alpha t if u0 is less than alpha t, but adding something. Now what are u1t, u2t tildes? So u2t, u2 tildes are defined in this way. It is beta if ui is greater than this, ui if it is like this, and if alpha if it is less than this one. This is replaced by r, this is not replaced, this is replaced by r. So it depends on un plus 1. If it is greater than r, it is less than r, or it is between minus r and r. Okay. Now you consider the modified problem, and you can show that ut lies between alpha t and beta t, and u prime t less than r. So this is what is the main theorem. In order to show this theorem, we need every solution u of the problem satisfies 11, prove 2 pages. Problem has a solution for this. We define an operator equation and show operator T1 is well defined, 1 page. T1 is completely continuous, 1 page. T1 is compact, 2 pages. Use Schauder fixed point theorem to show T1 has at least 1 point half page. So this is what is the framework in order to show that the modified problem has a solution. Now comes the main part here. Main part here is, in order to show that alpha t is less than or equal to beta t, that requires little work. Okay, that is not easy, and in order to show that, you have to work really hard. Okay. Now let me show you my second result. This time I'm assuming a pair of 2 solutions. Okay. And I'm assuming that this pair satisfies these conditions. And my function satisfies Nagumo condition with respect to alpha 1 beta 2 and alpha beta, replaced by alpha 1 beta 2. And then if these conditions are satisfied, so what I'm assuming, condition H1 and H3, and I'm assuming that this time I have not one pair of solutions, lower and upper solutions, but I'm assuming there are 2 solutions, upper and lower solutions. Okay, so if these conditions are satisfied, then you have 3 solutions, u1, u2, and u3. Okay, what I'm trying to tell you, that in order to prove this one, once again you have to modify the function. Once the function is modified, write down in the operator form and show that T2 is completely continuous. Rest of the proof is same as theorem 2. Instead of using Schauder's fixed point theorem, this time you have to use degree theory. Now you can continue. Instead of using 3 solutions, you can assume pair of 3 upper and lower solutions, and you can show that there are 5 solutions. So this way you can continue. What I'm trying to tell you, it depends on the number of solutions you have, the number of solutions you have, or the number of pair of solutions you have, you get for the first pair one solution, and for every additional pair, you get two solutions. So you can once again, you can get any number of solutions. Now, I'm going to give two examples how this theory works. Before that, I'll just mention that the results I have shown you can be extended easily for higher order differential equation. So this is my nth order differential equation. This is my general differential nonlinear part. This is the part which contains the singularity. Ut is phi t over the initial interval, same initial conditions, except this time it is from 0 to n minus 2. Same condition, except here you have n minus 2, here you have n minus 1 of derivative, and then you have un minus 1 infinity is b. Phi 0 is a0, ai is, all these ones are constants, b and c are in R, and a is greater than 0. Okay. Here, mi's are non-negative constants, so you can generalize it to any differential equation with more complicated delay. That is what is the idea. So what I want to mention, that what I have shown you for second order, you can extend it to nth order without any problem, and just you have to modify the proofs and you get the results. Okay, this is my first example. Use second derivative minus u prime plus 1 over 1 plus t to the power 4 tan inverse ut, u square t minus 1 square root ut over 2. This is my initial condition, 3 ut minus u prime t is 4, and u prime infinity is 0. So for this differential equation, my qt is 1 over 1 plus t square, tau 1 t is 1, tau 2 t is 2, t over 2. My function is minus u prime plus 1 over 1 plus t square, arc inverse, whatever it is here, I have written down. A is 1 over 3, which is positive. This is what is why we need here, that this should be positive. So if you divide this one by 3, you get 1 over 3. That's how this is positive. Phi t is 4 over 3, and tau is 1, and c is 0. The minimum of this, tau 1 is 1, tau 2 is t over 2. So minimum of this one is 1. Now, one of the hardest problem is how to find the upper and lower solutions. Okay. And those of you have heard the name of Luther Kohlrausch. He was the king of numerical mathematics. I asked him the question, if there is any scheme to find upper and lower solutions. He said, no, you have to keep on waiting until you find it. Now, there are some papers which are related to construction of upper and lower solutions. However, all the papers are theoretical. We have also written some papers, but for a given problem, it is very hard to construct upper and lower solutions, so you have to keep on searching. What I'm trying to conclude, upper and lower solutions, somehow you have to keep on. It is something like solving a non-exact differential equation, finding the integrating factor. Unless you find, you cannot solve, you cannot find the solution. Same thing is here. You have to find somehow the lower solution and upper solution. For our differential equation, alpha t as minus t and beta t as t plus 8 over 3, this works as a lower solution, this works as an upper solution. This is the verification. that it is a lower solution and upper solution. This is the verification that it satisfies the Nagumo condition. It satisfies the required condition that this is finite. This part is finite. This part is infinite. So all this is required, whatever is in the theorem, and hence we can conclude that this problem has a solution. We are not talking at all about the uniqueness. We are talking only about the existence. If you need uniqueness, you need much more. Let us see another example. I wanted to draw the graphs of this one, but somehow I could not do in the time. This is second differential equation. This is the boundary condition, the initial condition. This is the condition at infinity. Here qt is 1 over 1 plus t squared, tau 1 t is 1. This is my nonlinear function, right hand side. And a is 3, which is greater than 0. Phi t is t squared, 2t plus 1, and c is half. So all these ones are there. In this case, you choose your alpha 1 as t minus 4, alpha 2t as t over 3. You will see that it satisfies. So this is one lower solution. This is second lower solution. You will see that all conditions are satisfied. All conditions in the theorem are satisfied. Choose beta 1t as this and beta 2 as this. Again, two solutions, and show that all conditions which are in the theorem are satisfied, and hence you can conclude that there are three solutions of the required differential equation, and whatever is needed. The given problem has at least three solutions. Now, let me mention that we try to generalize this one to higher order. We were successful for the fourth order. You see, there is a difference. Here I am considering this type of problems. Okay, you have to, third order differential equation, considering 3-point, really 3-point problem. So we were successful in doing that, but for higher order, we were not able to do. On time scale, we were not able to do. In recent literature, I have seen somebody has extended for fractional differential equations. So I will say that there is a scope in this type of work. Here I have taken just in the differential equation second derivative. You can replace the second derivative by a linear operator, and you can just consider the solution second order linear differential equation. You can just assume that the solutions of the linear differential equations are strictly positive or strictly negative, and then repeat the everything. So all this is possible. Different type of nonlinearity, different conditions of nonlinearity, certain things have been done. Here, I have not assumed that the function is discontinuous with respect to the dependent variable. If function is discontinuous with respect to dependent variable, you require entirely different types of technology, the mathematics. So all this has been done, and it is available in the literature, but still there is a scope. For example, as I mentioned, that we could do for second order for discrete problems, we could not do on time scale, and for higher order, we don't know how to do it. So with this, I will end my lecture. If you have any question, I will be happy to answer.
Is there any question? Comments or remark?
Well, I have a question.
Sure.
Okay.
Okay, thank you for your presentation, Mr. Agarwal. You, as far as I know, I'm not from this area. First of all, I should mention that I am a professor at marketing, but I learned about you thanks to Mr. Köksal. He mentioned about you, and he said very good things about you. I am the founder of Association of Ethics in Academia in Turkey. I founded an association to promote and to increase awareness about ethics in Turkey. We do different activities to promote awareness about ethics. First of all, I want to thank you for producing so many quality papers, and I want to invite you for an interview with me, and I'd like to put the interview on YouTube channel of our association. If you agree, I'll be very pleased. And my question is, how did you manage to produce so many quality papers in your life?
Well, it is 50 years. I left home in 1969. I sleep with the book, I get up with the book, and my biggest strength is my students. You see, I have worked almost with 600 researchers all over the world. Okay, what I do, whatever problem comes to my mind, I pass on to my students. Okay, and whatever idea comes, I tell them that perhaps you can try this way, and it works. Okay, independently, I have written, I will say about 200 papers, and I have written almost 5 monographs on my own, but major work is in collaboration with my students. It works beautifully. You see, in research, there are several stages. If you are a student, you are dependent on the supervisor. Okay? Whatever he says, you have to do. What I'm trying to tell you, that your research starts after you get your PhD degree. Before PhD degree, you are doing only whatever your supervisor is doing, because he knows the best. Okay? So your first stage is that you are a good student. Your second stage is you start your independent work. Okay? Try to contact the leading mathematicians in your field. Send your work. I used to send my work to everybody who was leading mathematician in the field. Okay? Sometimes they reply, sometimes they don't reply. Okay? So that is your second stage. The third stage is you have research scholars. Okay? I treated my research scholars as my own children. I used to take my food for lunch. I used to take to my office, and I will ask my student whether he has taken the food or not. If not, I used to give him the food. Okay. I used to treat them very politely. I used to, so they appreciate what I have done. Okay. So for everything now they are doing, I have not made them dependent. They do independent work. They do guiding students, but they appreciate what I have done in their life. Okay. So that is the third stage. The fourth stage is you should invite the people. So Emir came under that category. After Emir came, almost 20 people came. Almost I have helped 10 people from Turkey. Okay. And they all appreciate whatever I'm doing, or whatever the way I handle them, or whatever way I treat them. Okay. Just I will show you this monograph. Oh, sorry. It is reverse. I should show here. That is very strange.
Worse. Now it's
Anyway.
okay.
Anyway, you see the third name. The third name is Abdullah Ozbekler. He came to me 3 years back. This is another monograph. This guy came to me from China. This is another monograph. What I'm trying to tell you, I try my best so that when they go back home, they don't repent that they went unnecessarily and they have wasted time. Okay, I expect that they work hard. When Emir came, he published 2-3 papers, and very recently we have published one paper. He came almost 10 years back, not 10 years, 15 years back. So still my contact is with him. So this is fourth stage. The fifth stage is the professors in other universities should recognize you, and they should write to you that they want to work with you. Okay. So from Turkey, from China, from Korea, from America even, lot of people have come, they have worked with me. So what I am trying to tell you, that if you are active and you are continuing in your life, you will be successful. It is difficult, but it is not impossible. Okay? So this is the way it goes. But if you are thinking only what you are doing, okay, then it is very limited, because your mind is limited. I don't mind if my student writes that you have done something wrong. I will immediately try to see what I have done. If it is wrong, it should be corrected, whether it is me or somebody else. So that's what is the way it goes. Now, my interest is in history of mathematics. I have written many articles. I'm writing another article on Pythagorean figurative numbers. It will be about 70 pages paper. I wrote about irrationality. That was 60 pages paper. I wrote about computers. Okay. I have written 3 very big articles. So I am writing nowadays popular articles. So keep yourself busy. That is what is first thing. Second thing is just try to help the people as much as you can. That is the only way in life, nothing else. By the way, just to let you know, I have been to Turkey at least 10 times. Okay. And I have given lectures in many conferences in Turkey, many universities. What is most important, I don't care what is internal politics, but I care how people behave with me and how I behave with them. I always get very warm welcome, and perhaps you may not be knowing, I will tell you, the best place in Turkey where to eat kofte. Do you know best place? Just opposite Blue Mosque, there is a restaurant, a small restaurant called Sultana Kofte. Okay, I have eaten there at least half dozen times, and it is always very good. Just continue working and keep on helping. That is what is the
then you can help us to promote ethic and to increase ethical awareness in science, academic ethics. Could we do an interview with you?
Yeah, you can interview. Let us wait, because for coming few days I am very busy. Today I am giving lectures at 3 places in 3 conferences. I have already finished one. This is my second, and 11 o'clock I am giving in Kosovo. Okay, so you write to me email, we will fix it sometime.
That's okay. So I'll get your email from Emir Köksal.
Yeah. You can
Thank you very much. Thank you very much.
And I try to reply within 24 hours. Okay.
Thank you very much, John.
Okay, Emir, have a nice day, and
Thank you.
I wish you all the best. And I want to see you, Professor, very soon. It is already too late. So if you need any recommendation letter or anything, let me know. Okay.
Thank you very much for your talk.
If you want, I can write directly to your rector. Okay.
Thank you very much for your talk, and I would like to thank you very much for attending the conference as a keynote speaker and present my best regards. I just have one question concerning your the talk.
Mm-hmm.
Which numerical method gives the most accurate for solving delay differential equations?
You see, there is a problem. Let me, I know your interest. Let me go back to one of the slides. And that is what is the most important part. You see here, x double prime x t square, right?
Right.
Now, t square is strictly less than t in the interval 0 to 1. Agreed? So you take I'm just taking just 4 points. T0, 0, T1, 1 over 4, 2 over 4, 3 over 4. T4 is 1, right? Now you are going to substitute Ti here. In this one, you are going to substitute Ti, right? This is the normal second order scheme. Okay? But you notice that T1 square, what is T1 square? Is 1 over 16. But 1 over 16 is not one of the grid points. So how can you compute this? You cannot compute this. Remember, number of equations is 3, but the number of unknowns are 1, 2, 3, 4, 5, 6. In other words, at T1 square and T3 square, you need to compute the value first. How? With using the values at the neighbor points, right? So some sort of interpolation is needed. Okay, in 1973, this was my second paper. What I did, I used linear interpolation. Computing the value at 1/16 with the help of 1/4 and 2/4, etc. Okay, and it worked. And then in this paper, I used spline. Okay, but how to use in general, I don't know. Okay, so this is a problem. Okay, because convergence, etc., that has to be studied very properly. My argument in 73 was just use this one, use interpolation, and then you get the answer. Okay, in this one, of course, I did some convergence, etc., but that was not enough. Okay, so if you want, you can, I will send you these two papers. Okay.
Okay. Thank you very much.
You're welcome.
Is there any other question? No question. Thanks again for attending this conference as a keynote speaker.
Thank you.
Wishing to meet in other
Okay.
international conferences again.
Yeah, definitely we will. Okay, keep on writing to me, okay?
Okay.
Okay, bye.
Bye. Okay, dear participants, I present my appreciates all of you for participating in this session. So I'm ending this session right now.